again to the Nambane Academy. I hope I am audible enough. By just greeting me, then I will be able to say hi to you back. Kindly say something to me so that I can be able to know that I'm audible enough. Please. Anyone? Can anybody say something that I'm audible enough? Okay, no, thank you very much. Then I'm going to get straight into it without wasting any time, because now anyhow we started late. It's 18:49 now, so I don't intend keeping you long, but we need somehow to finish everything that we started off. Now, as a quick recap, we tried to explain in detail the scientific meaning of what is work. It's where now we explained that work is now the product of force, displacement, and cos theta, where theta now is the angle between the surface and the force. And we basically said all the things that we have, this can be 0, this can be 180, and then it can also be 90 degrees. But now the question was, when should I be able now to apply 0? We said now this is when force and displacement are in the same direction. Force and displacement are in the same direction. In the same direction. This is key because in the examples that we are going to do, we'll need to apply this. Hence, I'm saying let's quickly have a recap of everything. So once we have the recap of that, we will be able to understand fully. And then we'll use now 180 if the force is in an opposite direction. Force is in an opposite direction with displacement. And then we said 90 will be now for perpendicular forces. Perpendicular forces. And remember, we said the work done by perpendicular forces will also be 0. But now we further broke it down into the details. So that is the basic summary that I did. We said it's key for us to always draw our free body diagram. It's key for us also to know how to calculate the work net. And then we said we can easily relate Newton's second law with the information that we have. So by so doing, it allows us to be in a position of answering all the questions related to how best can we calculate work. So this was the last example or a problem or a scenario that we spoke about. But now remember, the topic is called work, energy, and power. So we explained the concept work in detail. So what is it that we need to do now is further extend it to explain another concept, which is energy. And the question is, how best can we now relate the work and the energy? Before we do that, we need now to understand fully that we need prior knowledge from grade 10. Why specifically grade 10? Because in grade 10 is where we deal with different concepts that are related with energy. So before we can talk grade 12 content, we need now to link grade 10 work with what we are currently doing. So if you have questions, kindly show by a raise of hand, then I will stop, then we'll address your question. So the prior knowledge we need is, we need now to be able to explain what is energy, different types of energy, what is mechanical energy, and therefore the law of conservation of energy. So it's things that we should have been exposed to in grade 10. So the link thereof allows us to incorporate the information of grade 10, because the examiner can ask anything that is related to work, energy, and power. So we need also to refer to grade 10 work. Hence, I said this is key. This is important now for us to know. And remember, no need to worry if I'm too quick for you. The video will be available at the very same time. The PDF will be shared with you. So for the purpose of time, I'm going to be quick. Just try to be with me. Then we define energy as the ability to do work, which is measured now in joules, and it's a scalar quantity. That is very, very important. So it's the ability to do work. It is measured in joules, and then it's a scalar quantity that we need now to understand fully. But now we have different types of energies. So the very first energy that we have, I will start with this one as number one. We have what we call potential gravitational energy, or normally we call it potential energy. We also need to know the definition thereof. When I look at terms and definitions we have for grade 12, it's not given as part of the definitions, but because the assessment guideline says anything from grade 10, 11, and 12 that has to do with energy or a link between 10, 11, and 12 will be assessed. So for closing the gaps of not being shocked when we come across a question that says define potential energy, we should be able now to give the correct definition. So potential gravitational energy is defined as the energy the object possesses due to its position to a relative reference point. So it basically says how high or how low is our object in our frame of reference, which will be the ground in this case. So it is basically the energy that an object possesses due to its position. That is very, very key. The equation that we are familiar with, which is part of the formula sheet, it's EP is equals to mgh, g, which is our gravitational acceleration, 9.8 meters per second squared, and then m, remember, it must be now in kg, and then height must be in meters. That is very, very important, because once you don't have the correct SI units, then you are going to have a challenge of not getting the correct SI units. So because it's energy, remember, it will also be measured in joules or just J. That is very, 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 very important. Now, moving further on, for the number 2, which will be kinetic energy. So kinetic energy, we define it as the energy an object has as a result of the object motion. So the object in this case now should be moving. So if the object is moving, definitely it must possess the kinetic energy. And the formula thereof is now EK is equals to half mv squared. So these are formulas that we know of. These are formulas that we usually use, but the key thing that I wanted to emphasize is the definitions of the two different types of energies we have. So the mass must be in kg, and then velocity must be in meters per second. So if you are given your velocity in in kilometers per hour, definitely convert your energy to meters per second. That will assist a lot. Now, mechanical energy We also define it as the sum of the gravitational potential energy and kinetic energy at a given specific time or point. So this mechanical energy allows us to talk now of grade 12 content. But generally, this also comes from grade 10. So we need also to be able to state the conservation of mechanical energy. What must happen? Be able to state, this will be around 2 marks, and also be able to apply. So what is my key idea here? My key idea is the how part, the application. That is where my interest is. Stating will not be a problem because it will be a level 1 type of a question. So if it's a level 1 type of a question, then it's easy for me to give or state or define the conservation of mechanical energy. So the conservation of mechanical energy is defined or it states that the total mechanical energy in an isolated system remains constant. Basically, it sounds the same as the conservation of linear momentum. So the total mechanical energy in an isolated system remains constant, or we can even say now it is conserved 100%. So that is now the part of stating. Let's look into the application thereof. This is very, very key because we can only apply the principle of conservation of mechanical energy when the statement or the information that is given to us supports these 2 or 3 things that I want us to be aware of. The first thing is energy is conserved when there is no frictional force. So bullet number 1, we can only apply if now no friction. That is very, very key. You cannot just apply. So once friction is there, automatically it says you cannot apply conservation of mechanical energy. If they tell us that there is a resistance in the case of a parachute or a person now diving from a sky, then it says if now we don't have no air resistance, is then that we can be able to apply. That is very, very key. Or even when they tell us now the resultant force acting on the system is 0. That means now the system is isolated because the net force is equals to 0. Remember, that is how we define an isolated system. A system in which the net force is equals to 0. So we can only apply, I repeat, if we have a situation where we are told that anything that has to do with friction is not there. So when I read my statements, when I try fully to analyze the statements that are given, then it will assist me in terms of, is it possible for me to work with principle of conservation of mechanical energy? If yes, what is the contributing factor or the condition? The condition is that no friction, no air resistance. That is very, very key. There are questions that I came across some time back. The question will be, explain why mechanical energy is conserved. Definitely it will be conserved because there is no friction. It will be conserved. The resultant force acting on the system, it's 0. So let's kindly address that and know exactly where we can be able to apply the conservation of mechanical energy. So I'm going to pause a bit just to check if there are any questions. If there are questions, I will allow that because now I want to move further on. but I just need to allow us to have a discussion. It should not be a one-way traffic. So I'm waiting for you to ask me something related now to the different types of energies we have and how we link the content from grade 10, as well as the two formulas, the mechanical energy and thereof the conservation of mechanical energy. If there's anyone who's clear, kindly say we fully understand. If there's no one who's saying so, then I can easily move forward. So I'm just going to allow you to say something related to the few slides that we went through. Anyone? Just to confirm that we are still together. Ponyani? So no questions so far. Okay, thank you very much. And now, with the conservation of mechanical energy, the exam situations where we'll be expected now to apply is for objects that are moving vertically, objects in an incline, pendulums, roller coaster, and now the last bullet is very, very important. It's where we are going to link momentum and energy. Remember now, in the final examination, what happens is each concept or all the topics can be now asked in a form of linkage between the two. So we can link any topic with any topic in paper two, in paper one, because what happens is with mechanics is basically throughout the question paper of grade 12 paper one. So it's easy for us to combine something of momentum with energy, momentum with a projectile, momentum with your anything that is moving. Basically, we can be able to combine the two. So in this case, the most common one, it's how we link momentum and energy. So that's the reason why I chose now to add that. So I'm going to explain basic scenarios. Will not necessarily do the calculations thereof, because the calculations is what I expect us to do in the next session fully. So now we are just explaining the basic concepts, because once our foundation is solid, believe you me, we can answer all possible questions. So now, moving forward, it brings me now to example number one, or scenario number one. So scenario number one is for the objects that are moving vertical. So that means up and down. But the question should be, when I read the question, of which I want us to go through it together, there are few things that I want us to understand and maybe focus more on. A ball of 2 kg is dropped from rest at point A. Determine the maximum velocity of the ball at point B just before impact, and now ignore effects of friction. Very, very key. Ignore, let me get a highlighter for this. Ignore the effects of friction. That is very, very key. Because what does this say? This basically says I am now in a position of applying my conservation of mechanical energy. So by that already I can be able now to fully know that the very first step that I must take in performing this calculation, it's now what? It's analyzing with the correct data, but the fact that I am told that ignore the effects of friction, definitely it says I will be able to apply the conservation of mechanical energy. Fine. So key things for data. Remember from projectile motion, we said an object, if it's dropped, it basically says V initial must be equals to 0 meters per second. Very, very key. So it's things that now we're linking the knowledge we have. So with the knowledge we have from previous topics, we are now incorporating it in this type of questions. So the very first one is if it's dropped from rest, we know V initial will be 0. Hence, I don't have any other calculations given here. But I am told also that I have the height here, which is 4 meters, V initial, which is 0. The question is, what will be the V final at this particular point when delta H is equals to 0? So applying will not be a problem because remember we did say that this part here will be the conservation of mechanical energy. So it's EP plus EK at point A, EK plus EP at point B. And remember, all these other equations now are given in the formula sheet. So we should not worry, we should not over stress it that the information will be given. So for the conservation, we say it's the total. So it's the total of mechanical energy at point A and the total mechanical energy now at point B. So by so doing, definitely we know that we are in the right direction. Let's move now to scenario number 2. Scenario number 2 is now for an object that is on an inclined plane. So for an object that is on an inclined plane, obviously we have the part of which is the top and then the part now of which is the bottom. But the question should be, will I be able to apply the mechanical energy here, the conservation of mechanical energy? Yes, I should be able to do so, but let's read the question and fully understand. This you can practice later when you have the PDF just to check everything. But because you can see already, I only have the formulas, the approach, I don't have any calculations being done. So when we do the exam type is then that we will explain all things in detail. So let's move on. It says a 2 kg ball rolls at 3 meters per second on the ground A. Determine the maximum height the ball will reach at point B. Surface AB, it's frictionless. That is what I want us to emphasize. So frictionless basically means I will be able to apply now what? Apply conservation of mechanical energy. Very, very easy. So it means I will not be in a position of losing. I will not be in a position of losing the direction when I'm answering the questions, but definitely I will be in a position of, I know I must apply the conservation of linear momentum. Mepo Ponyani, the platform is yours. I see your hand is up. Ye- Okay. Good question. Thank you very much. You can lower your hand such that next time when you have something to ask, then I can definitely see. Thank you. What happens is, if once they start saying a rough surface, let's say maybe if in this case surface AB is frictionless, but now the examiner decides to say, but AB it's a rough surface, ne? So let's say that is what the examiner is now saying instead of a frictional surface, a frictionless surface. So it basically says we cannot apply conservation of mechanical energy. We can only apply conservation of mechanical energy when we have a frictionless surface, or if we are told that ignore the effects of friction. So once we are told that ignore the effects of friction, once we are told that frictionless surface is then that we can only apply the conservation of mechanical energy. I'm trying to accept few people that are coming in. Yes, now part of us. So once it says rough surface, we cannot apply conservation of mechanical energy. But once we have an information that tells us that there was no friction at all, then it means we can apply conservation of mechanical energy. So I will just emphasize it here to say, once we are told rough surface, do not apply conservation of mechanical energy. So this will be the biggest mistake that we do. This will be the biggest mistake that we do. So in an exam, I've came across a lot of people of not understanding this particular concept of we can only apply a conservation of mechanical energy if we do not have friction. That one we need now to emphasize. So is there any other question? Are you clear, Ponyani? Thank you. I'm moving on, guys. There is somebody here. I just want to mute them. They did not read the rules of the meeting, so I guess we are learning as we move on. So now with scenario number 2, I believe we are done. Let's now look into scenario number 3. Scenario number 3 is a pendulum. We came across a lot of this at times, but it's one of the nice questions that you find in an exam. So remember, I am not answering questions. I am just sharing with you the strategies or the key things that you need now to analyze or understand when you are working with a question. So we are taking it bit by bit such that we are able now to answer it correctly. Now we have a pendulum. So it says in the absence of friction, very, very key. What did they say again? No friction. So if there's no friction, what will I be able? It says to me, I must apply conservation of mechanical energy, 100%, because of this information here. So once there is no friction, I will repeat, I am in the right direction if I apply the mechanical energy. Because there are questions surely you have came across. They ask you now, use energy principles, because it's topics that you have done at school. Use energy principles. And the question is, when do I use, or which one do I use? So already we are building towards now answering the most complex questions. So if you know what to use, obviously your data will be based on the information that is given. It will be the information at A, it will also be the information at B, and then everything will be right for us to be able to answer this particular question. Now, on this one, it's where I said now we are going to link momentum with energy. So remember, with momentum, we had an opportunity of explaining different types of collisions. We had a position of explaining what is elastic collision. We're in a position of also explaining inelastic collision. So if you check here, we have a pendulum here that is swinging now into this particular direction, but now it's going to collide with a specific obstacle or an object. So it says to me, while the pendulum is swinging in this direction, just before the collision, I am going to apply now the conservation of mechanical energy. Just before. Because once it collides, let's call this one A, and then we can call this one B. So once object A collides with object B, it's no longer conservation of energy, but it's now what? It's now conservation of linear momentum. Remember, linear momentum, we only work with objects that are horizontal, according to the definition, as well as our exam guidelines. We work with 1D objects, so they must be in one dimension. So once they're in one dimension, it says A and B. Now I am going to treat them using the conservation of linear momentum. That is very, very key, because you get a lot of questions where there is a collision. You get a lot of questions where there is application of the two, because what happens is we understand that majority of our learners fail now with a multi-step calculation, calculations. And guys, be ready for these multi-step calculations. Multi-step calculations, what it basically says is use of two or more principles or equations, or even equations. So you will be expected at times to use two different equations for you to get to your final answer. So in this case, I say principles because it will be the conservation of mechanical energy and now the conservation of linear momentum. So for linear momentum, the emphasis now should be collisions. That is very, very key. And if you check the definition of conservation of linear momentum, it says the total linear momentum in an isolated system is conserved. Isolated system. When you check now the how we state the conservation of mechanical energy, the total sum of mechanical energy in an isolated system is conserved. So by so doing, it says fully 100%. It's easy for us now to link our momentum as well as our energy. So I'm going to pause a little bit and then allow you to comment on this. Anyone? Any comment, suggestion, inputs? If it's clear, then just say clear so that I can know I will be moving on. Olebogeng? Yes, Mr. More. Scenario number 4. Yeah. Thank you very much, Ntate Moreng. That is very key, because now we are working with basically the same object throughout. So the mass should be conserved as well. I fully agree with you, Minir, because once a mass becomes an unknown, majority of our learners now panic and don't know exactly what to do. So I didn't want to say a lot of it, because we are still now talking of the same 2 kg throughout. 2 kg scenario 1, 2 kg scenario 2, and then 2 kg scenario 3. And now for this scenario number 5, we must also add that mass is conserved also. So it means the mass will cancel out. That is very, very important for us to do, colleagues, or even learners. Sorry, I'm used to saying colleagues, so I end up saying it here also. But nonetheless, it's fine, because this was a learner support. But Ntate Moreng, thank you very much for the input. Let me now move to work energy theorem. So we are linking the concepts of work together with the concepts of energy. The first part is taken as it is from the exam guideline. So with work energy theory, there are 2 things that you must also be able to do. The 2 things that you must be able to do is now to state the theorem and also now apply. That is very, very key. So stating the theorem is basically 2 marks that each and every one of us should be able to get. It says the network done on an object, is equal to the change in object's kinetic energy. It doesn't need me to have a rocket science to understand exactly what they are saying. They are basically saying the work net, which is now the total, is just equals to the change in EK. It's as simple as that. But now the majority of us, we fail to fully understand what is the network. So hence that Nambane started with explaining each simple concept of how to get the work net. So remember, the work net is the total work done on an object. So this must be now from what? From all the forces that are doing work. So this should be the sum of all forces that are doing work on an object. That is very, very key. So it's basically sum of all the work done by different forces. That is basically what we are saying here. So it means for me to understand it easy, I must be able to calculate the individual forces. So the first thing to do, very easy, draw a free body diagram. That is now the first section of this particular sessions that we are busy with. Draw the free body diagram. identify the forces that are parallel, because we did say that now forces that are parallel are actually the forces that are doing work. I think we did say something here. Forces that are parallel to the surface always do work on an object. So we only rely on the parallel forces. So once we have identified our parallel forces, then we are in a position of explaining or calculating as per required. So now with work energy theorem, it's just basically the application of work and the energy that we spoke about. So now I want to emphasize this, the change in kinetic energy. So for the change in kinetic energy, it will be half mv squared final minus half mv squared initial. So if we do this, we can easily see that we are working with only one mass. Let me write it down. It will be half mv squared final minus half mv squared initial. Maybe I must also remove this just to create a nice space for each and every one of us to see. Okay, this here should be final. Let me write it nice. It's half mv squared final minus half mv squared initial. So remember, we are working with speed here, so there's no need for direction. So everything you substitute now as positive, because work, remember, it's a scalar quantity. Energy is also a scalar quantity. But just remember our direction. We get it now from where? From the 0 and the 180 that we choose our angle on. So my emphasis is this. For one to know that we are working in the right direction of work energy theorem, it's easy for us to say, but for me to apply work energy theorem, I must now have one object. So once I have one object, it is now another nice key, another strategy of me saying there are chances that I can work with. And I want to emphasize here, because already we spoke of conservation and work energy theorem. So for us to apply conservation of mechanical energy, we said the keyword, no friction. But now, once we have all the forces that are doing work, so if I am going to draw a free body diagram for this situation here, force applied, Fk, and then I must have Fw or Fg. I want to explain to you with this, because we are working with work net. And remember, the first topic or the first concepts we did was work. In the video, we explained that we need to draw a free body diagram. So now that I have identified already that there is frictional force, already I won't be able to apply the conservation of mechanical energy. Already it is restricting me in order to apply the conservation of mechanical energy. So once friction is there, definitely the other option that I have will be applying work energy theory. The questions are going to be specific. The questions are going to be challenging in a sense that you need to know exactly which principle are you going to apply. So if there's no friction, conservation of mechanical energy stands a better chance. If there is friction, automatically work energy theorem must work. But now, I want to say here, or maybe I should not say it as yet. I will say it as we move along. So basically, this is all about work energy theorem. We are also expected to apply it to objects that are horizontal, vertical, and inclined planes for both frictionless as well as rough surfaces. But now, once we have a frictionless surface, then it means we can be able to apply conservation of mechanical energy. So this is all about work energy theorem. State and apply. Conservation of mechanical energy, state and apply. So if we are able to state, definitely we should be able to apply. So moving further on, we just linked now conservation of mechanical energy or energy with work energy theorem. So we are going to move it a little bit because the exam guideline also says we need to know what is the difference between conservative and non-conservative forces. So this is where majority of us have a problem or a challenge. So I'm going to explain it fully and in detail and also give the examples thereof. So what the exam guideline says is a conservative force, a force for which work done in a moving object between 2 points. Okay, let's make it smaller. Between 2 points is independent of the path taken. What are they exactly saying when they say independent of the path taken? Let's do this. Consider now a free fall. So for this free fall, I am going now, first thing, I'm going to drop it. So if I drop it, what is the direction of my FG? The direction of my FG will be downwards. But now, what if I decide now to throw it up? So I know that if I throw it up, it will go up and then come down, and then let's say it returns now to the starting position. But the direction also of FG, whether it is going up or down, what happens? It is now in the same direction, which is downwards. So if I drop an object that is in a free fall or a projectile, FG downwards. Even if I send it up or throw it up until it reaches the maximum height, the direction of FG, it's still now downward. If it's moving down, the direction of FG is now still downwards. Hence, we say, regardless of the direction it takes, it is independent of the path. So whether it is going down, whether it is going up, it still remains in the same direction. So hence the definition thereof says it's a force of which the work done in a moving object between 2 points is independent of the path taken. So the examples thereof are gravitational force, electrostatic force, magnetic field, and elastic forces in springs. So once we understand this, that a conservative force is independent of the path taken, and remember, the examiner is looking for the keywords, so it must be a force for which work done in a moving object between 2 points is independent of the path taken. So please use your terms and definition. Know this, the reason why we need to know this, last year it was assessed, majority of learners got it wrong. So the feeling is the examiner will consistently ask the definition of a conservative force and a definition of a non-conservative force, or there of anything that relates now to a conservative and non-conservative force. Let's move to non-conservative force. This is key. This is what I want us to look into. So there's a word that we are usually aware of, which is fat. So once I see fat in the statement, in the information that is given, I definitely know I am working with a non-conservative force. But Ntate Nambane, why are you saying fat? Because now I want to explain that a non-conservative force is a force which the work done in a moving object between 2 points depends on the path taken. So these ones depend now on the path taken. That is very, very important. So I am going to make a simple sketch here. Let me put it down here on a rough surface, and I apply my force in this particular direction. So what must I do? Let me draw a free body diagram. Fn, Fw, force applied, and then my Fk. But for the very same object, I decide now to change the direction of my force applied, still on the rough surface. What happens when I draw my free body diagram? I will have my Fn, I will have my F applied, I will have my Fw, I will also have my Fk. What is it that I can see here? Okay, it's easy for me to see that these forces here are the forces that are doing work 100%. But look at the direction of my friction if this is the direction of the motion. And if this is the direction of the motion, what does it do? It also changes direction with now what? With the direction of the motion. So we say friction is a force that opposes the direction of the motion, and it's parallel to the surface. And it's true. Fk parallel to the surface, Fk parallel to the surface, but it's depending now on the direction that we take. So explaining this concept, it basically says a force which work done in a moving object between two points depends on the path taken. So Fk, the direction of Fk, frictional force, depends now on what? Depends on my direction of the force applied as well as the direction of the motion. That is what they actually explain. That is actually what they say here in terms of the definition. So why did I come up with this analogy of fat? We came up with the analogy of fat, the reason being I want us to be in a position of understanding exactly that fat will assist us not to forget the type of forces that we are working with. So once I remember in an exam that when I have fat, I actually mean that I must have now my friction, I must have now my air resistance, and then I must also now have my tension. So once I have tension, once I have air resistance as well as friction, definitely I am working with the non-conservative forces. So that is where majority of us lose marks, because at times we don't know what to use and what to apply. So once I have identified that in the statement, in the information that is given, then I have fed or any of the given forces, definitely I will be able now to apply the conservative force. So this now brings me to this key summary. This key summary, please, when you get the PDF of this particular document, kindly go to it, perform a couple of questions. So when you perform a couple of questions, you will see why the design of this particular summary, why I decided to have this summary, because the question always comes: use energy principles to calculate, use energy principles to calculate. So I usually say, for you to answer all the questions, there are two possibilities in these three principles we have. So these three principles, is three of them. These principles, it's three of them. So once we have the three of them, the question is, which one will be more applicable? Ladies and gentlemen, this is now the science. This is us ensuring that we perform at maximum, we perform at 100%. This is what differentiates a level 2 learner to a level 5 and a level 6, 7 learner. So once you get this slide correctly, when you get it, analyze, and you will see, once you start practicing more questions, everything will be nice and clear. Remember, as a hint, two principles always works. Okay. As a hint, two principles always works. Always. I am putting my head on the block and say always. If it's not always, kindly come to me and tell me that that number, you did not give it to us the right way. But I definitely guarantee you, two principles will always work. Now the question is, between the two principles that I have, which one will be more applicable? Now, work energy theorem. This is now a hint. Always works, regardless of the information that is given. It might require you to perform it twice, but it always works. So now, option number one for me will always be work energy theorem. But the mistake that I'm going to do with work energy theorem is the examiner at times doesn't ask me to draw a free body diagram. That is now the challenge we have. So it says to me, ensure that your free body diagrams are correct, because with work energy theorem, we need now to identify all the forces that are doing work. Then we need to draw a free body diagram. So once the free body diagram is correct, the identification of forces is correct, then it's easy for me to apply work energy theorem. But now, if I am going to use work energy theorem and I find that now I have friction as one of the forces that I have identified, automatically conservation of mechanical energy will not work. So if the conservation of mechanical energy will not work because I have friction, then it means the only option that I'm left with will be work done by non-conservative force. Questions, guys? Please. This is the key slide that I wanted us to get to. questions, please, or inputs before I move further on? Kindly ask something. Anyone, please, or say something. Alota? Yes, sir. Not a problem, sir, because the A can be either for a resistance as well as the applied force. Thank you very much. 100%. Any other questions? Any inputs? Thank you very much. Now, work energy theorem always works 100%. And then now, if I have identified my forces and I find that I have friction as one of the forces when I'm working with work energy theorem, then it basically says I cannot use conservation of mechanical energy. And if I have applied, I've identified that work energy in work energy theorem, the free body diagram that I used, there is no friction. I am told it is a frictionless surface. Then automatically I can now apply the conservation of mechanical energy. So this is key in a sense of knowing exactly which energy principle to be able to apply. So once you know which one to apply, believe you me, you will be in the right direction. So for me, guys, the basics are done. The only thing that we need now is we will look into tomorrow. We'll just have to discuss our schedule tomorrow. Send me the questions that you feel that if for you personally, if we can address this particular question, you will be able to understand the concepts of work, of energy. I'm going to say a few things about work power now, but now it's key that we understand the energy principles, because that is where the majority of marks are sitting, or where we can be able to get the maximum marks. So I'm going to request privately, send me the questions that you feel, just a snapshot of the question. If you know it's from which year, you can do that, such that at least I have a cleaner source for us to work with when I prepare the slides now for tomorrow. Guys, the last aspect here, it's power. I will say with power, there isn't much to discuss, because we need now to calculate work done first. And once we have work done, it's easy now to calculate for power. But what does the definition of power say? As per the exam guideline, it says power is defined as the rate at which work is done or energy is expended. So this is the formula. You'll also get it from the formula sheet. So remember, once we have time, it's easy for us to say rate at which work is done or energy expended. So now what else do we need to do? Calculate the power involved in work done. So basically it says we need to calculate work. So once we are able to calculate work, then we can come and use this particular equation. I must emphasize our time must be in seconds. That is now very, very important. And then perform calculations, and then calculate the power output of a pump lifting a mass, lifting water through a height of constant speed. So already you can see as things that we need now to perform calculations. We need now to apply the equation of work. So the only thing that I'm going to do in this section is just to choose questions that ask us to apply each and every bullet that our exam guideline wants us to do. Because now when we choose questions also, that is what I want us to be aware of. When we choose questions that we want to address, let's ensure it's questions that closes the gaps or opens your eyes for the whole chapter or the whole topic as it is, because in so doing, whatever the examiner is going to assess is not going to be anything outside this particular scope. So if we do a calculations of power but we don't do an example where there is lifting of water, it means we haven't done justice to this particular topic. So guys, it is exactly 1954. So I'm not sure if there are any questions. If there isn't any questions, I will likely remind you that the link to the register will be sent immediately after this, but don't leave the meeting yet because I am sending it into the chat, because I don't want to share it in our group, because the people that did not even attend the meeting will automatically automatically fill it in. And we are keeping numbers, colleagues, guys, because I'm working with getting ourselves a nice sponsor for data. So they need consistent people that are coming into the academy, that are joining the classes consistently, so that when we give you at least that SIM card of Vodacom, SIM card of Telcom, at least you know that all the lessons, you can access them for free through this platform as well as our YouTube channel. So I'm working very, very hard, guys. Hence, I just don't want our things to be out in the open. But kindly, if the classes are assisting and they're opening a few or closing few gaps, please tell friends more. The numbers we have likely for the sponsor now to be a part of us. So I'm going to close this section and send a link to the chat. Kindly fill it in. But before that, thank you very much for all your efforts. So I'm planning to have, because it's a holiday tomorrow, I'm planning says that let's have an earlier session maybe. So preferably the guys that are here, just tell me which time do you think will suit you best, so that I can be able to prepare something. Don't forget also to send the questions to my personal number. Then I will prepare something so that we know that we have finished with work energy and power. Then we can move to rates of reactions and chemical equilibrium. That will be around 80 marks in the June exam. Any questions, any inputs before I close the session? Mbele, good evening. Okay, are you in our WhatsApp group? Okay. When you fill in the attendance register, I will, what was the word? I will add you to the group, and then the PDF will be shared in the group, and then the links to the video as well. Okay, so just ensure that you fill in the right details when you fill in the Google form. Thank you. Any other one? Okay, guys, for me then, thank you very much. Don't leave the meeting yet. I'm just about to send the register to you. Thank you.